Okay, in this video I'm going to talk about an equilibrium. We're just going to do some simple numbers here with a equilibrium that works out with two reactions that are both possible but don't happen at the same rate. Here we have the forward reaction A plus B going to form AB, and the reverse reaction AB splitting back up to go back to becoming A and B. And we're going to say the forward reaction is favored. It happens 4 times faster than the reverse, and we're going to say, just to give us some numbers to work with, that 40% of the particles will undergo the forward reaction, and the reverse reaction, 4 times slower than that, means 10% of those will do that. So let's just look at this mathematically and see how this equilibrium sorts out. See how the populations of A, B, and AB end up at equilibrium. So imagine I have A and B, and I have 1,000 particles of each. And I have AB, and we're going to start with none of it. So I'm going to say 40% of my 1,000 particles will react in the forward reaction. So this is going to go at 40%. And 10% will come back. So let's see what this looks like. Here, 40% of 1,000 is 400. So these are both going to go down by 400, and this isn't going to do anything because it's at a population of 0, so it'll just increase by 400. So that means I'll end up with 400 ABs and 600 remaining. And we could say that's after 1 instant or 1 second in time. And this is just going to continue. So now 40% of 600 is 240. And now, so that's going to increase by 240, but now we have the reverse reaction coming along as well. So we have 400, so we're going to reduce that by 10%. 10% of 400 is 40. So we're getting times 40% here to give us this number, and we're getting times 10% here to give us that number. 40% of these particles will go forward, 10% of these particles will come back. This one is 4 times faster than this one. So 600 down 240, up 40 will be 400 in the next instant. And this guy will be up 240, down 40, so we're up to 600. Now, getting a little closer to even here, but not quite there yet. These guys, again, are going to react away in the next instant, 40% of them. That's 160, 40% of 400. That's going to create 160 new of the compound AB. And 600 here is going to decrease by 10%, so that's going to be 60. These numbers are working out pretty easily. So this is going to be 300 of this left over when it loses its 160 and gains its 60 back. Same here. And then this guy is up to 700. We are still not at equilibrium. We can see that the population of AB is still declining while the population of the compound AB is increasing. Again, another 40%, that's 120. 120. And 10% of 700 is 70. Oh, sorry, they're going to get its 120 first, then lose its 70, gain its 70, gain its 70, and these 120s are losses. So that means that this is going to be down 50, 250, 250, and this is going to be up 50 to 750. And now I'm going to cheat with the calculator here. 250 times 0.4 gives me down 100, down 100, up 100. And I'm just going to keep going with this until we get at least a little bit closer. And then we're going to go down 75, up 75, up 75. So some instant later, we are at 275. No, 225, I mean. And this guy's going to be at 775. And we keep going, 225 times 0.4, 90. So down 90, down 90. What we can see is the rate of these reactions is getting closer and closer together. We're getting closer to equilibrium. As the population of A and B gets lower and lower, the fact that it's going faster is compensated for by the fact that the A and B, individual particles are becoming depleted. Alternatively, as the AB gets built up, the fact that it's a slower reaction is being compensated for by a greater population. And as we can see, we're not there yet, but we're headed to equilibrium. So we're at 210, not 210, that's not right. Being a little lazy with the calculator here. 213, 213, and so what's the difference there? We're up 12? Yeah, 12, so this is 787. Okay, so we're getting closer and closer to an equilibrium condition here. 213 times 40% is 85. And 787, I'm going to call that 79. And we're almost equal, but we're not equal. We might be seeing slight changes in our system still at this point. Here we're going to be down 6 to 207, 207, and up 6 to 793. So now we're at 83 here, 83. Down those amounts, add that 83 in here, and similarly 79, 79, 79, so at 211, not 211, 203, 203, and plus 4 is 797. And I can keep going here. I will, I guess, because I'm on a video, I might as well. This is going to be 81, 81, and this is going to be 80. 1. And what we can see here is we are practically at equilibrium. This guy's going to decrease by 1 each time. This guy's going to increase by 1 each time until you can keep doing the math you want. This one hits 200. And this one hits 800, and then as you can see, these guys, 40% of them will react, creating 80 new ABs, and here 10% of this will react, and it's gonna feel or observe like the reaction is stopped, when really the reaction continues. It just continues in a meaningless way. The amount created is the same as the amount destroyed, and ta-da, we are at equilibrium. This is obviously not an even equilibrium. We can see that since this reaction was faster, these populations got lower, and this population got higher, so that when we consider the two factors that are coming together to form the overall rate of reaction, we consider the speed of the reaction and the concentration. And when we take those two things both into account, the reaction rates become equal. So because this reaction was faster, it had to have a lower population, and because this reaction was slower, it had to have a higher population to make up the difference and make the overall reaction rates equal. So that's what it looks like when one reaction is faster than the other. When that happens, it's not like it completely wipes out the backward reaction or the reactants, but what we can see is we set up an uneven equilibrium that reflects the pace with which each reaction naturally happens.